Let me start our first session from the presentation of Professor Emanuel Peled of his wonderful work.
Okay, good evening. I'd like to thank first the organizing committee for inviting me to give this talk. I will talk today on nanoscience and nanotechnology used in batteries and fuel cells for transportation. I'll give some introduction on the need for increased battery energy density and reduced cost in order to get the driving range of 500 kilometers. Then I will present three issues on some technology and science of using nanotechnology for battery materials and fuel cell materials. First one is 3D high-capacity silicon nanowires, anode for lithium batteries, then core shell nanoparticles for lithium-sulfur batteries, and core shell nanocatalysts for fuel cells. So here you see the Toyota Prius plug-in, and you see the battery over here. This car can drive about 20 kilometers on the battery, then it switches to the gasoline engine. And I think that even in Israel, they start selling it today. And this is the Toyota fuel cell car. You see the yellow one is the high-pressure hydrogen storage. It's about either 350 bars or 700. I'm not sure about that. It's a beautiful car and has the driving range of about 500 kilometers. What you see is what is the prediction or estimation of penetration into the market of various car types of electric vehicles. First one is the hybrid, that we have Prius hybrid, and we have other hybrids, then plug-in hybrids, and then full battery. And there are only few real battery cars. The one most popular today is Tesla, that costs something around $100,000. And after that, fuel cell cars will come into the market. And there is some expectation that, or prediction that at 250, most of the cars on the road will be some type of electric cars. And here you see the problem of the mass. And today, electric cars are using lithium-ion battery technology that we have in laptops and cellular phones. The issue is that they don't have enough energy. So if you want to run 500 kilometers, then it should, the mass of this car will be 2 tons, and that's not practical. So there are 4 systems that can deliver potentially the 500 kilometer range. One is fuel cells cars that we have a couple of hundreds or even a couple of thousands today on the roads, most of them demonstration units. And this is the most progressed one today, the only one that really gives you the range. The other that is lithium sulfur, lithium air and sodium air. Lithium air and sodium air are infant, and it may take 20 years to see if they can be developed into a real battery. But lithium sulfur has more progress, and we expect it to be developed in some years. So some information how lithium-ion battery works. It has an anode. Today the anode made of graphite, and we insert or integrate lithium cation into the graphite during charge, and they insert them into the solution during discharge. And we have some metal oxide, lithium metal oxide cathode, that gets the lithium cation into it, and electrons during discharge, electron going this way, and during charge going this way. On the top of the graphite anode or any anode, there is what we call solid electrolyte interface, which is a nano-size solid electrolyte, very important. So first I will talk on 3D high-capacity silicon nanowires, anode for lithium batteries. I'd like to acknowledge my colleague, Professor Potolsky. So his group is synthesizing these nanowires. Professor Golodnitsky, Dr. Friedman, and the student Davidi and Schneier. So why do you like to change graphite into silicon? And there are, I believe, thousands of researchers all over the world trying to improve lithium-ion battery by increasing the capacity or energy of the cathode and by increasing the capacity and energy of the anode. In this talk, I'm talking only on the anode. And the reason we are looking into silicon, that silicon can accept or can deliver 10 times more capacity in terms of per hour or any other charge unit when you compare it to silicons, to graphite. If it gives you 300 units and silicon gives 4,000 units. So there is a problem there. We like to get many thousands of cycles of charge-discharge, but silicon intercalates with about 4.4 lithium atoms, and during this process they got volume expansion of over 300%. And then when they insert lithium from the silicon, it goes back down by 200%. So this is a real problem that has to be overcome. Then we like to have high rate, and our novelty is the growth of three-dimensional silicon nanowires into and on the top of carbon matrix. Previous research in this field just grow silicon forest on flat substrate, but we did it all over the volume of the carbon matrix. So we synthesize 3D high-capacity binder-free silicon nanowires, and we took a carbon paper, and it consists of a fiber-based network, and we grow the silicon nanowires inside and outside this matrix. Therefore, you get quite high capacity. And we analyze, characterize this anode by different means. And what you see here on A is a micrograph of the carbon paper. It is made of fibers about 7 or 6 micron thick. And B is the position or growth of silicon nanowires on this carbon paper. But most importantly is D micrograph. Then you see here, this one is the carbon fiber, and you see here a lot of wires inside. So this is a cross-section of the paper, and you see that we can deposit silicon nanowires into the paper and therefore utilize the full capacity or the full volume of the substrate. The thickness of the diameter of the average diameter of the nanowires is about 230 nanometers. And when we run EDS, we see only silicon because it's quite thick one. Now this is the micrograph of the nanowire. And we have, it's a core shell type. We have very tiny crystalline core and amorphous shell. And by XRD, we found that we have at least 93% of the mass of the silicon is amorphous, and we believe this is very important and give us, enable us to get a long cycle life and good performance. We test the electrochemical way into these anodes. We build what we call in electrochemistry half cells, is silicon nanowires versus lithium, and cycle them, and then a complete battery. What you see here is a capacity in terms of milliampere hour per gram of silicon versus cycle number. So we cycle 200 times. And here's the capacity in terms of milliampere hour per square centimeter of electrode area, and we got about 4. This is very important. There are many papers in Nature and Science and others showing excellent performance of silicon nanowires, but they're using 0.1 milliampere per square centimeter. So it's very good to write a paper. It is nothing for a real battery. But we had in mind that we need to fulfill the target of lithium battery, And normally in what you have in your pockets on your laptop, it's 4 milliampere per centimeter square. And this is the value that we were looking for. On the left side, you see that we got 3,000 milliampere per gram of silicon, which is about 70% of the theoretical value. Now, the question one, why would the capacity drop with cycle number? So there are two options. One, what is commonly written in the literature is that we have pulverization and loss of contact of the silicon nanoparticles or nanowires, and therefore we lost capacity. But we came to the conclusion this is not the case. When we reduce the current density to 0.1 milliampere, we got back the capacity, and actually here we lost, after 200 cycles, only 20% of the capacity. I think we can lose less. This is a capacity of a real battery made of silicon nanowires and cathode lithium iron phosphide, which is very popular cathode in lithium-ion batteries, and we got quite stable 70 cycles. That's very important to show that it can work in a real battery and not just in half cell. So to summarize this section, we are able to build 4 milliampere per centimeter square electrode, which is important. We even were able to get 8 milliampere per centimeter square. In this case, we can sandwich our anode between two cathodes, and this is very important. I don't have time to show you, but we have shown very low irreversible capacity of about 10%. This capacity is used to build the SCI on the anode, because the lithium-ion batteries are assembled in the discharge state, and when you charge it first time on the graphite, on the silicon, or on the silicon anode, or any anode, you first have to build SCI. Before that, you cannot charge the battery. And we're able to run it at very high rate, but we can charge and discharge in 20 minutes. And we've also shown a battery. Now, a few words on the solid electrolyte interface, because it's a very important issue. And what happened is that I said we build, or not we, the lithium-ion battery are assembled in the discharge state. The first step is to charge the battery, and you have graphite or silicon. You push electron from the cathode into the anode, and this comes into the solution, reduce all the solution components, which is solvent and salt, and you have a precipitation of solid electrolyte particles. And you see what happened here. There are different particles that precipitate on the surface of lithium or carbon or silicon, and it's lithium fluoride, oxide, carbonate, semicarbonate, some polyolefin. The issue is that we have to stop the electron going from the electrode into the solution. If you don't stop it, you have continuous corrosion and you don't have a battery. Now, all these nanoparticles are cation conductors, and these conduct lithium cations. So when you charge or discharge, lithium cations go from here to here and comes into the solution. Now, this is happening in all lithium and other alkali metal batteries. The anode is completely covered by SCI, a few nanometers thick. It's 2 to 5 nanometers. And if you if you do not design this condition in the battery is dead. It can't function. So this model was published in 1979, and today all the experts in this field are using this model to analyze their results regarding lithium batteries. So the SCI is a key component to affect safety, self-discharge, cycle life, operating temperature, and power. Therefore, we study the growth of SCI and its resistance on the silicon nanowires. So what you see here is a micrograph after 1 cycle and after 11 cycles of charge-discharge, and you see that there is some precipitation on the nanowires. And then the nanowires grow from 270 nanometers to 370 by 100 nanometers during 11 cycles. But we run it 200 cycles, and the battery 70 cycles. So probably in our long cycle life test, the SCI thickness grows to hundreds of nanometers. That's our expectation or estimation. Now here you see that the composition of the film deposit on the nanowires. We have fluoride and phosphor atoms coming from the reduction of the salt, which is lithium hexafluorophosphate, and oxygen and carbon coming from reduction of the solvent. As I said, we have lithium carbonate, same carbonate, and ketones, or whatever. When we clean it, we can wash these anodes by water, DMC, ethanol, and water, and we clean out the SCI, we just dissolve it, and instead of this kind of composition, we got only silicon and carbon, and we don't have fluoride and phosphorus, and silicon goes up to 22 to 83%. So you see that we have some soluble SCI, water-soluble SCI on this fiber or nanowires. Now we measure the thickness of the SCI during 11 cycles. It goes from 22 to 72 only during 11 cycles. And as I said, we run it to 200 cycles, and it goes much more. So in summary, the silicon nanowires anode, summary of this section, has 1,300 milliampere per gram of anode. It is 4 times larger than graphite. And we run it 200 cycles, and only 21% loss of capacity. So under our test condition, the most severe causes of capacity degradation are increase of the SCI thickness, resistance, and resistivity. And we have to minimize it in order to get good cycle life. Next issue is the lithium sulfur battery, and a piece of history. The first lithium sulfur battery that was assembled with porous carbon loaded with sulfur was built in my laboratory and published in 1989. And this is the discharge and charge curve for this cell. We were not able at that time to solve the problems of cycle life, and we got internal shorts and other problems, and so the sulfur was soluble in the electrolyte and attacked the lithium anode, and we stopped it, and we came back to it only 3 years ago when we have new ideas how to solve these problems. So this system is quite complex. We start with sulfur, and we reduce it during discharge. We got down in polysulfide, which partially soluble. These are soluble in the electrolyte, and come down to lithium sulfur. When we charge it, it goes back to sulfur. And there are 2 problems. One, this soluble polysulfide attack the anode, passivate it, and create lithium sulfide on top of it, and corrode it. And the other one is that when we reduce sulfur into lithium sulfide, we have 80% volume change, volume increase, and this cracks the cathode. So the idea how to solve these 2 problems. So we had some thought to use what we call mixed conductor matrix cages, and to encapsulate the lithium sulfide, to start with the discharge state, encapsulate lithium sulfide into these cages, and when we charge it, the volume will decrease, and the polysulfide will not come into the solution. So I'd like to acknowledge Dr. Mital Alon, Dr. Katie Friedman, and Professor Golodnitsky for this section. So what we do, this is a simple schematic way. We took lithium sulfide, and we cover it by a shell, tiny shell, nanometer shell of solid electrolytes that conduct lithium cations and some electron conductors. So lithium cation can go out, electrons can go out, but polysulfide or sulfur cannot go out. So when we charge it, the volume of the lithium sulfide goes down, and you create some void, and this is pure sulfur inside the shell, and when we charge it, it goes. What's happened here? Okay, thank you. Okay, so these are small cages, but it's only a schematic picture of them. Now it does move. Stuck.
Mm-hmm. Mm-hmm.
Okay, בסדר, אני משתמש בזה. So here you see ESAM images, and some of it on the left side is what we do. We have two options. One, to completely melt the shell without melting the lithium sulfide, because lithium sulfide melts at above 900 Celsius, and we're using shell that melts at about 700 or less. Or the other one is just sinter it and to get מה לעשות עם זה? Okay. So we build from this kind of a cathode, sulfur cathode, that we assemble it in the discharge state when we have lithium sulfide. So first time we charge it and not discharge it, and we got very stable cycle life, and about more than 50 days still running. But the major issue here is that we have close to 100% Coulombic efficiency. That we mean if we charge it by 100 capacity unit, we get back 100, and not like in the case of solubility of polysulfide that attacks the lithium, it's between 90% to 98%. So this is quite good evidence that our concept is right, and polysulfide are not coming out from the cages. Now, the next one is the study of core shell catalyst for oxygen reduction reaction. And this is for fuel cells. I would like to acknowledge the student Dima Kaplan, Dr. Meital Gur, Dr. Mital Alon, Steva Tsizin, and Dr. Burstein, and Dr. Rosenberg, and Dr. Popov. Now, the issue is that you see here a scheme of a fuel cell. This is one cell. The heart of it is a proton exchange membrane or proton conducting membrane, which is mostly Naphthalene in all fuel cells. On both sides of the Naphthalene, we have a layer of catalyst. I'm making it very simple. And these catalysts are nano-sized. It's mostly platinum or platinum alloy. And on one side, we feed with hydrogen, one other side on oxygen, got water, and got electrons that going into the load, into the device. So this way, fuel cell works. And the issue is that the major cost of this system is the Naphthalene membrane, cost today $500 per square meter, and the platinum catalysts were very expensive. So these two components takes something like 70% of the cost of the fuel cell. So we or other researchers like to reduce the cost of the platinum. Here you see the stack. It's about 200 or 300 cells in this one cell, and here you have many cells in stack, and this is what sits in the car. Now, the concept is to use a core shell nanoparticle concept. Why is that? Because if you're using nanoparticles, let's say 5 nanometer of platinum, the bulk of the platinum doesn't work. Only the surface serves as a catalyst. So why do we have to use platinum in the core if the outer monolayer just work? So we are picking some less expensive metals like ruthenium, iridium, and other ones, and deposit on them monolayer or submonolayer of platinum or platinum alloy, or build small nanoparticles of platinum or platinum alloy on the surface of this core. So this is a very nice example and very STEM EDS micrograph, and this is the particle, and this is the line for the EDS, and what you see, the blue one is the ruthenium particle, and we deposit platinum on as a shell. As clearly you said that you have platinum outside and ruthenium inside, that's very clear evidence that we are able to really get what we like, a platinum shell on ruthenium core. Now, when using XPS and EDS, it's another evidence, and we have also another electrochemical evidence for that. And for example, in the platinum on ruthenium, we get 80% platinum atoms at the shell, and 30% platinum atoms in the core, and that's we have close to 3 times more platinum on the surface on the shell than in the core. And the same for iridium. This is platinum on iridium, and we have again 3 times more platinum on the shell than in the core. So the last thing to do is to measure the activity. That's nice, but it's not enough. So we purchased Johnson Matthey high-spec 8000. This is the best catalyst we were able to purchase, and we compare our catalyst to this one. And there are 2 parameters for comparison. One is practical, it's economic, it's dollar value, and we measure kinetic mass activity in terms of ampere per gram of platinum or ampere per dollar. And we see that we get, with this catalyst, 2.5 times more activity, higher ampere per gram of platinum than the commercially available catalyst. This is about the same. So this is economic parameters. Now, scientific parameters is the real activity and the surface activity. What is the surface activity of this catalyst? And again, when we measure the activity in terms of ampere per square meter, Wills per square meter, then you see the kinetics ability of the catalyst. And again, we have that our catalyst is 3 times more active than the high spec. So the platinum that we deposit in a submonolayer on iridium, we get better catalytic. That means there is some of better catalytic activity of the combination of iridium underneath the platinum or nearby. And thank you for your attention. On graphite or any carbon, you can intercalate in units, milliampere hour per gram, about 370, or let's say on 6 carbon atoms, you can put 1 atom lithium. In silicon, in aluminum, and tin, you can put more. In silicon, on each silicon atom, you can place 4.4 atoms of lithium. As a result, that's phase diagram.
Carbon is lighter. So
no, but you need 7 atoms of carbon for 1 atom of lithium. The real parameters is milliampere hour per gram. This is capacity per gram of electrode. So the graphite is 373, silicon 4,400 or something. Aluminum is about 3,000.
Any other question?
Over there.
Hi. So what's the criterion for choosing the internal part of the, I'm referring to the last part of your talk, ruthenium or iridium? Okay. Why them?
The issue is that in the fuel cell, the chemical environment is very tough. We have an Nafion membrane, which is actually sulfuric acid in terms of activity. It's about 1 molar sulfuric acid. So, and it runs at about 80 Celsius. And you have hydrogen on one side, oxygen on one side, a lot of peroxy radicals, so it's tough environment, very corrosive one. Now, so you have to pick up that the core will stand the corrosion environment. You can't use nickel. You can't use cobalt. You can use alloy. For example, ruthenium nickel or platinum nickel you can use, and we did it. Even get better activity. Let's say platinum with about 20-30% atomic of nickel or cobalt is better catalyst than pure platinum. But the core has to stand the environment, the corrosion environment in the fuel cell.
And does it have to be inert? I mean, not react with platinum or?
Not reactive, yes. And it has to be electronic conductor.
Okay, so these are the criteria.
Yeah. There are some ceramics can be used. If you have ceramic that is a very good electronic conductor and can stand 1 molar acid at ATC and can stand hydrogen on one side, oxygen on the other side, it also can function as a core.
But that will be more difficult, I think, to produce.
How did you synthesize the core shell nanoparticles?
How what?
Synthesize. How did you synthesize the?
By electroless deposition. You take a carbon powder, first synthesize nanoparticle for ruthenium or iridium, and on top of that, we electroless deposit submonolayer of platinum or platinum alloy. It's not fully covered. You see the XPS and the XPS, you see also iridium or ruthenium at the shell. Also, we have electrochemical evidence that it's not completely covered, but let's say between 50 to 70% platinum and the rest is the other metal on the surface.
Thank you very much. Let us thank our lecturer.